Welcome. Have you ever listened to a guitar solo and felt like the notes were floating, creating a sense of space, depth, and rhythm? From legendary Pink Floyd riffs to modern ambient guitar textures, the delay effect is a must have in a guitarist's arsenal. But what if I told you this magic sound is nothing but pure math and signal processing? Welcome to this tutorial where we will decode the science behind delay pedals. What is a feedback comb filter? How is delay created using a digital memory? And how we can implement this effect using Python. This entire process will be described in this tutorial. Let's dive in and uncover the math behind the music. If you have never heard of a delay pedal in action before, let's fix that. Here's a clip of Pink Floyd's legendary delay usage in action from songs like Run Like Hell and Another Brick in the Wall. Listen closely. Do you hear how each note repeats and fades away? Interesting, isn't it? That's the feedback loop in action. The sound is being stored, delayed, and played back multiple times, creating a rhythmic echo that defines the song's feel. But how does this work mathematically? Let's break it down. Here are some popular guitar effect pedals which are used very frequently by various guitarists. And you can see certain knobs and certain controls on these pedals, which will be explained later. The magic of a delay pedal comes down to a single powerful concept called the feedback comb filter. The core idea is simple. Take the input signal, in this case Xn, delay it, this is the delay part, and then mix it back with the original signal. So as you can see here, signal samples move in from this direction and they go to an adder and then they pass out and become the output. The output is then fed back to this block, which is called a delay line. This M represents how many number of samples will be delayed before they are allowed to pass through this block. And then this G is an attenuation factor, which is multiplied with the signal. And this is added back to the original input. And that's how this equation is formed. Xn is the input. This adder comes from here. G gets multiplied by this the output of this delay line. And the output of the delay line is nothing but output which is delayed by M samples. That's all there is to it to a comb filter. As far as visuals are concerned, you can see that input signal looks like this, let's say. And when it is passed through this entire system, it comes out from here. And what you see here is multiple replicas of this original signal, which are reduced in amplitude and are stacked horizontally one by one. And this is how actually a delay looks like. Now for comparison, I have shown a pedal here. You can actually see the controls, how they map to this filter structure. So when we are talking about time, we are talking about delay time, which can be set by this knob, and which is in fact controlling this delay line, essentially changing this number M. Then we have a feedback. This feedback knob is nothing but this G, which is going to attenuate the output of the delay line. And inside it is an adder. And echo is basically how much of this signal are you permitting in the original signal chain. So if you are giving a value of 1, then this entire feedback gets mixed with the input without getting attenuated. And since it's not getting attenuated like this, so the signal will not die down and there will be multiple echoes for a very long time. That's how this entire filter structure gets mapped to this delay pedal. As far as the name of the filter is concerned, it is derived from the fact, it is derived from the spectrum that it generates. The spectrum looks like a comb. Some frequencies are amplified and some frequencies are attenuated. And because of the shape of this spectrum, the filter is called as comb filter. Now that we know that math behind comb filters, let's look at how we implement delay digitally. A guitar pedal doesn't have infinite memory, so it needs to store past values of signal to play them back later. How do we store delayed signals? In Python, there's a data structure called array. That's how it looks. It is nothing but a chunk of memory in which data samples are stored, and these data samples are stored to specific memory locations, which are called as index. So for example, if I have to retrieve this number 12 from this memory, then the address of this space is called index, and that index is at 0. Similarly, if I have to retrieve this number 19, then the index to this number is 5, and I can specify in code that I want to index out this number 5, and it'll get retrieved. Python also uses the reverse indexing system. So instead of saying 0, 1, 2, 3 as memory locations, you can start from the other side, and you can call memory location 5 as -1, -2, -3, and so on and so forth. Now how this array acts like a digital delay line is that with every clock tick, these numbers are shifted right. So for number 12 to come out of this pipeline, it will take 6 clock cycles. And the 6 clock cycles are some time apart. So that time apart of these 6 clock cycles is the effective delay of this delay line. We will see this work in the code. So here is the plan. We will generate an input signal, which is a computer equivalent of a guitar pluck, which is a sinusoid note at 440 hertz, which is exponentially dying down, so that it will be multiplied by a decay factor. And then we are going to pass this decaying exponential through this filter structure and see how it behaves. Over to code.